You clap your hands. Sound. You hear it, right? Now, you probably think something traveled from your hands to your ear, like a thing moving through space, a sound wave moving from here to there. But I'm going to tell you something, and this is going to bother you. Nothing traveled, not one molecule went from your hands to your ear. Not one. What you heard was air colliding with air in a chain reaction, a molecular domino effect at 343 meters per second. See, the dominoes fall in sequence, but no individual domino travels the distance. Get it? That's what sound is. A pattern of collisions, not a thing that moves. Now, I know we usually say sound travels, sound waves. The wave moves from here to there. That's the language everybody uses. Teachers say it, books say it. Hell, I say it sometimes. And look, it's not completely wrong, but it's misleading. Why? Because it makes you think something is moving. Some object, some particle, some wave entity going from point A to point B, but that's not what's happening. And if you don't understand what's really happening, you'll be confused about sound forever. You'll think you understand, but you won't. Not really. So let me tell you what actually happens when you clap your hands. Your hands push air molecules together, they compress them. That creates a region of high pressure. More molecules packed into a smaller space than usual. Squeezed. Those compressed molecules, what do? They push against neighboring molecules. The neighbors get compressed. They push against their neighbors, and so on. Chain reaction. Boom, boom, boom. A wave of compression spreads outward. But here's the key thing, and pay attention to this. The original molecules, the ones your hands push directly, they don't go anywhere. They just bumped into their neighbors and stopped. That's it. Done. Think about a line of billiard balls. You hit one end hard, and the ball at the far end shoots out. Beautiful demonstration, right? But the balls in the middle, look carefully. They barely move at all. They just pass the energy along, like a relay race where the runners stay in place. Sound is exactly the same. Energy passes through the air. The air itself stays roughly where it is. Doesn't go anywhere. Each molecule moves maybe a nanometer. You know how small that is? A billionth of a meter. Tiny oscillation back and forth. Microscopic wiggle. But the pattern, the region of high pressure, that moves fast. See the difference? It's crucial. A sound wave isn't a thing. It's a pattern. A pattern of motion that propagates through a medium. But the medium itself doesn't travel. The stuff stays put, stays home. Now, when we say sound wave, what do we actually mean? What are we talking about? We mean a region of alternating high and low pressure, compression and rarefaction. The air bunches up, then spreads out, then bunches up again, over and over. Push, pull, push, pull. That pattern moves. The pattern has a speed. Why that speed? Where does it come from? Good question. Really good question. It comes from how fast molecules can collide with each other. At room temperature, air molecules are moving around at hundreds of meters per second. Incredible speeds. They're like tiny bullets, constantly colliding, bouncing off each other millions of times per second. Chaos. When you create a pressure wave, the speed it propagates depends on how fast those collisions happen. Hotter air, faster molecules. Faster collisions, faster sound. Simple. That's why sound travels faster on a hot day. Not much faster, but measurably faster. You can detect it. You can prove it. Temperature matters because temperature is molecular motion. That's all temperature is. Just molecules bouncing around. The faster they bounce, the hotter it is. Now, what happens in a vacuum? No sound. Why? Think about it. Because there are no molecules to collide. No medium to propagate the pattern. Simple as that. Nothing there. You can't have a pressure wave without pressure. And you can't have pressure without molecules. Can't happen. That's why space is silent. Not because sound waves get absorbed or fade out. Because there's nothing to carry the pattern. No chain of collisions. Nothing to bounce. Zero in science fiction movies. You hear explosions in space. Lasers going pew-pew. Spaceships roaring past. Nonsense. All of it. Hollywood garbage. There'd be silence. Complete silence. Unless you're inside a spaceship with air. Then you'd hear things inside the ship, sure. But outside? Nothing. Absolute nothing. A wave isn't a thing that moves. It's a pattern of movement that propagates. See the difference? It's crucial. Think about a stadium wave. You know what I mean? At a sports event, people stand up and sit down in sequence. The wave goes around the stadium, looks great, looks like something is moving around, but the people don't move around the stadium, right? Each person just stands and sits right there in their seat. The pattern moves, not the people. The people stay put. Sound is the same. The pattern moves through the air molecules just vibrate in place. They're not going anywhere, not traveling, just wiggling. Now, let's talk about frequency and pitch. What's the difference between a high sound and a low sound? What's really different? The answer is how fast the pattern repeats. How many times per second the compression-rarefaction cycle happens. That's it. Middle A on a piano is 440 hertz. You know what that means? 440 compression-rarefaction cycles per second. The molecules at your ear get pushed and pulled 440 times every single second. High notes? More cycles per second. 1,000 hertz, 2,000, higher. More repetitions. Low notes? Fewer cycles. 100 hertz, 50, lower. Fewer repetitions. But here's something people get confused about. The speed of the wave, still the same. Always. In air, at room temperature. High notes don't travel faster. They just repeat more often. Got it? The pattern moves at the same speed regardless of frequency. Now here's something remarkable. Timbre, the quality of a sound. You can tell a piano from a violin even when they're playing the exact same note. Same frequency. Same pitch. But you know instantly which is which. How? The answer is harmonics. Multiple frequencies happening simultaneously, all at once. When you pluck a guitar string, it doesn't just vibrate at one frequency. It vibrates at the fundamental frequency plus twice that frequency, 3 times, 4 times, and so on, all overlapping. All those vibrations create sound waves simultaneously. The waves overlap. They interfere with each other. The pattern becomes complicated, rich, textured. And that complicated pattern is what makes a guitar sound like a guitar instead of a boring beep. Your ear receives this complicated pattern of pressure changes. Your brain analyzes it. Incredibly sophisticated analysis, by the way. And you perceive timbre, you recognize the instrument. But it's all still just air molecules colliding. Just more complicated patterns of collision. Nothing mysterious, no magic. Let me tell you about echoes. You've heard echoes, right? What's actually happening there? You shout in a canyon, the sound comes back to you. Everybody knows this. What happened? The pressure wave spread out from your mouth. It reached the canyon wall. The wall is solid. Molecules packed tightly together. When the pressure wave hits the wall, it compresses the molecules in the wall. Those molecules push back. They're not going anywhere. They're part of the wall. So they create a new pressure wave going the opposite direction. Bounce. That's the echo. A reflected wave. The wall absorbs some energy, sure, but most of it bounced back. Same principle as light reflecting off a mirror, except it's pressure waves instead of electromagnetic waves. And the reflected wave? It's still just air colliding with air. The molecules near the wall collided, then those collisions spread back toward you. No molecule made the round trip. They all just bumped their neighbors. Now, sound travels at different speeds in different materials. Why is that? In steel, sound travels at about 5,960 meters per second, much faster than air. In water, about 1,480 meters per second, still faster than air. Why? It's not about the speed of individual molecules. It's about how fast the collision pattern propagates. In steel, the atoms are packed tightly, they're bonded strongly. When one atom moves, it immediately affects its neighbors. The pattern propagates quickly, efficient. In air, molecules are far apart. They have to travel a distance before colliding. The pattern propagates more slowly. Lots of empty space. In water, it's in between. Molecules closer than air, farther than steel. So the density and bonding of the medium determines the speed of sound. Not the speed of individual particles. The medium properties. Stiffer material, harder to compress, faster sound. Makes sense when you think about it. The point is, sound speed is a property of the medium, not of the sound itself. The medium determines the speed. Now, let me tell you something that might change how you think about conversation. When you talk to someone, your voice doesn't reach them. not literally, not the way you think it does. You vibrate your vocal cords. That creates pressure waves in your throat and mouth. Those waves exit your mouth. The air right outside your mouth compresses and rarefies. That pattern spreads, molecules colliding in sequence. Eventually, the pattern reaches the other person's ear. The air molecules at their eardrum oscillate. The eardrum vibrates. The brain interprets that as sound, as words. But none of your air reached their ear. The molecules are all local, completely separate. You didn't send sound to them. You created a pattern of collisions that propagated through the local air, and the pattern eventually reached their local air. It's like sending a message by telegraph. You tap a key in New York. Someone receives the message in California, but no electron traveled from New York to California, right? The electrical signal propagated through the wire. Different electrons along the way. Same thing with sound. The pattern propagates. The medium stays local. Here's another thing. Sound is incredibly inefficient. When you shout, the sound spreads out in all directions. A sphere of pressure waves expanding. The energy you put into the shout gets distributed over a larger and larger surface area. The intensity drops as 1 over distance squared, inverse square law, twice as far away, 1/4 the intensity. 10 times as far, 1/100th the intensity. It falls off fast. That's why sound gets quieter with distance. Not because the pattern is getting tired, because the pattern is spreading, the energy is diluting. Most of the energy you put into a shout is wasted. Only a tiny fraction reaches any particular listener. Terribly inefficient. When you use an amplifier, you're not making the sound travel farther. You're adding energy to create a stronger initial pattern. So even after it dilutes, there's still enough intensity to hear. Microphones and speakers work by converting between pressure waves and electrical signals. The microphone detects pressure changes and creates corresponding voltage changes. The speaker does the reverse. But at every stage, it's local. The air at the microphone isn't the air at the speaker. Can't be. The pattern gets converted, transmitted, and reconstructed. Music is the same. When you listen to a recording, the speaker creates pressure waves that mimic the original sound, but the air molecules in your room were never anywhere near the original performance. Never. The pattern was captured, stored, and recreated. The molecules are all new, local to your room. You know, there's something beautiful about this. Every sound you've ever heard was created locally, right next to your ear, inches away. The collision pattern came from far away, maybe, from across the room, across the street. But the actual pressure changes that vibrated your eardrum, those were local air molecules. Molecules that have been in that room the whole time. When you hear a symphony, the music is being recreated in your room by the speakers. The air molecules in the concert hall never left the concert hall. They're still there. And before recording technology, every sound you heard was created within earshot. Nothing could reach you from farther than sound travels in air. A few kilometers, maximum. That's why the world was quieter before amplification. The sounds you heard were limited by the natural propagation of pressure waves. Just natural sounds. Wind, voices, footsteps. Now, let's talk about something strange. The speed of sound is the speed limit for certain phenomena. You can't have a pressure wave travel faster than the molecules can collide. That's the speed of sound. Physical limit. But what if you move faster than sound? What happens then? You get a shock wave, a sonic boom. When an object moves through air slower than sound, it pushes air out of the way. The air has time to move aside. Pressure waves spread ahead of the object, giving the air warning that something is coming. But if the object moves faster than sound, the air doesn't have warning. The object hits the air before the pressure wave can get ahead of it. Boom! The result is a sudden compression, a shock wave. All the pressure changes pile up into a single sharp wavefront, very intense. When a supersonic jet passes, you hear the boom. That's the shock wave hitting you. Your eardrums get punched. It's not the sound of the jet's engines exactly. It's the sound of air being compressed faster than it can get out of the way. And that shock wave follows the jet. A cone of compressed air trailing behind. Anyone in the path of the cone hears the boom. The jet itself? The pilot doesn't hear anything special because he's moving with the shock wave. From the pilot's perspective, it's quiet. but on the ground you hear the boom. The collision pattern hitting you all at once. Here's another example. Thunder. Why does thunder happen? Lightning heats the air to about 30,000 degrees Celsius, almost instantly. The air expands explosively. Has to. That expansion creates a pressure wave, a very strong one. That's the thunder. The light from the lightning reaches you almost instantly. Light is much faster than sound. No comparison. The sound takes time, about 3 seconds per kilometer. So you see the flash first, then you hear the thunder. Always. Count the seconds between flash and thunder, divide by 3, and you know how many kilometers away the lightning struck. Simple trick. But what you're hearing is the pattern of pressure changes created by the explosive expansion of air. The molecules that got heated aren't the molecules at your ear. They just started the chain of collisions. Now there's a question people ask. If sound is just molecules colliding, why can I hear around corners? Good question. Light doesn't go around corners, right? You can't see around corners. But sound does. You can hear someone talking in the next room even if you can't see them. Why? The answer is diffraction. Sound waves have long wavelengths. Middle C on a piano has a wavelength of about 1.3 meters. Big wave. When a wave encounters an obstacle smaller than its wavelength, it bends around it, diffracts, spreads into the shadow region. Most objects in your environment are smaller than the wavelengths of sound you hear. Doorways, furniture, people. So sound diffracts around them. You can hear it. Light has much shorter wavelengths. Hundreds of nanometers. Tiny. Most objects are much bigger than that. So light doesn't diffract as noticeably. It creates sharp shadows. But sound? Sound bends around corners, spreads through doorways, wraps around obstacles. That's diffraction. Purely wave behavior. It's still the same collision pattern propagating. But the pattern spreads out as it encounters obstacles. You know, I've been talking about air. But sound works in any medium with molecules. Solids, liquids, gases, same principle. Even your body, when you hear your own voice, you're hearing two things at once. Sound traveling through the air to your ears, and sound traveling through the bones in your skull directly to your inner ear. Two paths. The bone-conducted sound is different. Different frequencies are enhanced. Lower frequencies, usually. That's why recordings of your voice sound strange to you. You're only hearing the air-conducted part. You're missing the bone conduction you usually hear. Everybody experiences this. You hear a recording and think, that's not what I sound like. But it is. That's what everyone else hears. You're the only one who hears the bone conduction. But it's still the same principle. Molecules colliding. Patterns propagating. Just through different media. Air versus bone. Here's something subtle. When I say molecules collide, I don't mean they actually touch. Not physically. Wait, let me be careful here. Atoms never touch. Remember that. Electron clouds repel. Electromagnetic forces keep them apart. So when air molecules collide, they're really approaching each other until electromagnetic repulsion pushes them apart. They never make contact. The collision is electromagnetic, not mechanical contact, pure electromagnetic interaction. But the effect is the same. Momentum transfers, energy transfers, the pattern propagates. So we can still call it a collision. Just understand what's really happening. Sound is electromagnetic at the deepest level, just like friction. Just like almost everything you experience in daily life, all electromagnetic, but we don't need to think about that to understand sound. We can treat the molecules as little balls that bounce off each other. That model works fine. Beautiful simplification. That's one of the nice things about physics. You can use different levels of description depending on what you're trying to understand. Different models for different purposes. For sound, thinking about colliding molecules is enough. You don't need quantum mechanics, you don't need to worry about electron clouds and electromagnetic forces, unless you're asking very specific questions. But for everyday sound, classical mechanics works beautifully. Now, let me tell you why all this matters. When you understand that sound is a propagating pattern, not a traveling thing, it changes how you think about communication. Really changes it. You're not sending messages through the air, that's sloppy language. You're creating disturbances that propagate. The listener reconstructs the message from the pattern of disturbances they receive. It's indirect, fragile, easily disrupted. That's why loud environments make conversation hard. Competing patterns interfere with each other. They overlap, cancel, distort. And it explains why perfect silence is so rare. There are always molecules, always collisions, always some pattern of pressure variation, never truly quiet. True silence would require a perfect vacuum or perfect stillness at absolute zero, neither of which exists in nature. Impossible. Even in the quietest room you can imagine, there's residual sound. Thermal motion of air molecules creates random pressure fluctuations. You can't eliminate it unless you eliminate the air entirely. So, sound is ubiquitous. As long as there's a medium, there's the potential for sound, always. And the medium doesn't travel, it just vibrates, passes the pattern along. That's its job. So, there you are. Sound isn't a thing that moves. It's a pattern of molecular collisions that propagates. The molecules themselves barely move. A nanometer back and forth, tiny oscillations, almost nothing. But the pattern moves fast. Fast enough to seem instantaneous over short distances, slow enough to measure over long distances. Just right. When you hear music, none of those air molecules came from the speaker. They were already in the room. The speaker just organized them into a pattern, choreographed them. When someone speaks to you, their air stays in their lungs. Your air stays in the room. The pattern of their speech propagated through the intervening air and arrived at your ear as a new pattern created locally, brand new. Every word you've ever heard was created inches from your eardrum by local air molecules vibrating in response to a pattern that traveled. Not the molecules, the pattern. Always the pattern travels, the medium stays. That's the difference. And that difference is everything. Strange, isn't it? That something so familiar, something you experience constantly every day, is actually so indirect, so removed from what you think is happening. You think you hear the world, but you only hear the patterns created in the air next to your ear. Patterns that might have originated far away, but were recreated locally by collision chains. Sound doesn't travel. It propagates, a chain reaction of molecular collisions. And not one molecule makes the journey. Not one. Zero. They all stay home. Now you know. Now you really know what sound is.